in any building is life-threatening, very, very frightening, and very expensive. Fire in multi-story structures is all of that multiplied. It spreads surprisingly rapidly. The effects are devastating. Fighting it particularly difficult and dangerous, and the immediate and associated costs to business staggering. It doesn't take many minutes for the loss to become substantial. This is a fire in a typical curtain wall building, a structure that has a light exterior cladding with a lot of glazing. Just 2 minutes ago, it was no more than the size of a match flame. In the short time it's taken to grow this much, someone might have discovered the problem and alerted the fire brigade.
Fire service.
Even though they swing into action immediately, it would still take them some time to reach the scene. Multi-story office buildings tend to be open plan, with little to impede the spread of fire. So, as they set out in their fire appliance, the blaze will be spreading quickly, consuming desks, computer terminals, photocopiers, laser printers, and perhaps a company's central nervous system, its accounts and customer records. In fact, it has been found that in these kind of buildings, more damage is being done more quickly than has been expected. Fires are wreaking more havoc than even pessimistic projections of loss assume. LPC scientists have been conducting this unique series of tests to measure and map the characteristics and behavior of fire in a purpose-built test rig. The intention is to establish how and at what speed fire spreads in multi-story buildings with curtain walls. The data gathered will help to inform architects, engineers, and insurance professionals of the precise nature of the risk and of the measures which need to be taken to minimize the risk of fire spread and consequent loss in such buildings.
The constructions that we now have in London and other cities, high-rise office buildings, you've got a big potential for loss, and it's a matter of time before we have a major loss, I guess.
The main problem is assessing the actual estimated loss exposure which we may face. It's trying to ascertain how much damage will be done to the fabric of the building, to the contents of the building, and whether there will be any consequential loss to the business.
The main problem in surveying a curtain wall building is probably one of recognition, in that it's quite difficult sometimes to recognise whether you're dealing with a lightweight or heavyweight type cladding system, and to recognise exactly what the materials are which are incorporated into the system. It's also, of course, the case that you can't see the fire stopping or the quality and the nature of the fixings.
There's no doubt that fire safety provision in high-rise buildings is sometimes flawed. The fire brigade arrived within 4 minutes of the alarm being raised at this 14-story office block at Basingstoke in 1991. They found a serious fire developing and flames already penetrating the curtain wall. The floors of the building were designed to be resistant to fire and did their job. So what caused the fire to spread so dramatically? Heat and smoke travelled through an unstopped service duct and up the curtain walling of the building. 46 fire appliances and 176 firefighters took 4 hours to control the blaze. The fire loss alone amounted to some £15.5 million. The consequential loss for businesses in the building was, of course, much greater. There are plenty of other examples of curtain walling being implicated in the rapid spread of fire in high-rise buildings. It was clearly time something was done about the problem. In this series of experiments by LPC scientists, a 3-floor section of a full-scale, multi-story building was actually constructed in one of the Boreham Wood laboratories. Dr. Jim Glockling is head of Special Projects Group, who have carried out the experimental work for LPC.
The rig is 10 metres in height and 6.5 metres wide. This allows us to have 2 complete scale floors on which to perform fire tests. It also allows us to have an underfloor area 2 metres high to build fires such as this one to evaluate fire break-in through curtain walling systems from the exterior. The rig is instrumented to ensure that the fires have the same properties between tests, and therefore we produce data that is comparable between tests. All the key components of the system are also instrumented so that we may evaluate how they fail and when they do this. Thermocouples, temperature measuring devices, are attached to all the components whose failure we are interested in. For example, they will be attached to the sides of the aluminium brackets, holding the system onto the floor slab, at various levels up the mullions and transoms, the grid-forming structures, and onto the glass itself. Additionally, heat flux meters located around the structure allow us to evaluate the rate of heat transfer through the curtain walling system, and a thermal imaging camera directed at the entire cladding system gives us global information of the temperatures and heat flux that the system is being subjected to. Catastrophic failure of windows and other components are recorded on camera and the time logged accordingly.
The fuel firing the test series is a crib made of wood and plastic, a mixture replicating the makeup of a typical office fire. Every crib will be the same, so that every fire will be the same. Except, that is, for one experiment, when actual office furniture will be substituted as a control test. And that will lead to some surprising findings. But we'll be witnessing test number 11, a typical fire in a typical curtain-walled structure. In this case, the source of ignition is a taper, but if this was real life, it might have been started by a small electrical fault. A careless piece of hot work by a contractor, or a heat source like a spotlight too close to paper. Probably no one would have spotted it yet. If it's out of the way, in a storage area say, it might not be seen for several minutes. In the test, the fire has been burning for about 40 seconds now. We'll return to the test fire during the course of this short video as the fire burns in real time. You'll probably be surprised at just how quickly a fire can spread between the floors with devastating consequences. But while the fire is quietly growing, feeding on oxygen and combustibles, and seeking new avenues to explore, we'll find out more about curtain walls. Dr. Jim Denny is Technical Manager of the LPC and Director of the FPA.
Modern office buildings are built to a fairly standard design, a steel framework with concrete floor slabs, and then hung on to the outside of the steel framework is usually some sort of curtain walling system. The floor slabs and the steelwork are well protected against fire. They provide good fire separation. The curtain walling system does not. It doesn't have to. It's designed mainly to provide protection against the weather. And modern office buildings are generally not close together at the high stories, so there's no possibility of fire spread between the buildings, and the separation is enough. Fire resistance is not necessary. The other big factor in modern office buildings is the open plan design, which means you can get rapid growth of fire, rapid fire spread, and large fires which easily affect the curtain walling system.
The LPC test has been running for just 3 minutes. The fire continues to grow, involving more of the crib and increasing the temperature in the enclosure. Already the internal panes of the double-glazed windows are starting to crack. The curtain wall of a multi-storey building consists largely of glazing held in place by a framework of horizontal members, the transoms, and vertical members, the mullions. Spandrel panels are opaque and run horizontally between the windows, concealing details at floor and ceiling level. The whole is kept in place by metal bracketing, which is attached to the concrete slab floors. The LPC test building faithfully reproduces the interface between wall and floor, as Jim Denny demonstrates.
What we've tried to do here is to reproduce a typical modern office building with a curtain walling system. The panes of glass in the curtain walling system are held in place on a metal frame. The metal frame is then supported on the building by aluminium brackets. As the framing is put in place and the panes of glass are put in place, fire stopping is added to provide a barrier to fire between the floors of the building. This goes all the way along the building, but there are, however, some gaps, particularly at the back of the brackets, where there are holes through which fire could spread up the building. And if a pane of glass should fail, and during the course of a fire, then the fire stopping could fall away, and this in turn could also lead to fire spread up the building.
The test has been running for 6 minutes. As the face heats up, sensors monitor precisely the amount by which it expands. Smoke is starting to leak through the curtain wall framing. Unless it is made of fire-resisting glass, which is expensive and therefore not common practice, the curtain wall affords a poor barrier to check fire spread.
If you built the office building out of a material like brick or masonry, it would inherently have fire resistance. It would withstand the effect of fire. A curtain walling system doesn't do that. It's glass. Glass allows the radiation to pass through the walling easily so that you actually have possibility of flames outside. The heat of the fire can also affect the transoms, the mullions and the brackets that actually form the curtain walling system.
The LPC test has been running for 7 minutes. The inner panes of the spandrel panels have started to crack, while cracking of the windows continues. From the outside, the obscuring effect of the smoke may make it look as if the fire is going out, but don't be fooled. That's far from the case, as this infrared image of the heat generated by the fire reveals. Any fire needs heat, fuel, that's combustibles, and oxygen to start and spread. Heat from the fire can be transmitted by conduction, radiation, or convection. All three are important when considering fire spread in multi-story buildings. Radiation from the fire causes nearby combustibles to become involved, and the heating of all surfaces within sight of the fire. Conduction of the heat of the fire through the metal frame supporting the curtain wall, a good conductor, causes it to heat up and weaken. Conduction through the glass causes stress, leading to cracking. But it's convection that most concerns us in considering the spread of fire in high-rise buildings. When fire breaks out, 3/4 of the heat in the blaze is spread by currents of hot air and gases. As the gases are hotter than the surrounding air, they rise, easily setting fire to anything they come into contact with. An open flue will provide a means of heat transmission and a source of oxygen. Flames, which can be at temperatures of 1,000 degrees centigrade and carrying products of combustion, quickly rise to the floors above, passing the heat onto new fuel. In a very short time, a small fire will become an uncontrollable blaze. The inner panes of the spandrel panels are beginning to fall away. So far in the UK, we've been relatively fortunate. Our multi-storey fires have started near the tops of buildings, like at Basingstoke.
Floors of Jakarta's 25-storey central bank, the fire left...
But really, that's just luck. A fire can start at any level in a high-rise structure. Fires in Pretoria, Philadelphia and Los Angeles started at mid-levels, resulting in fire spread up several floors of the building.
As smoke continued to billow into the sky, a police helicopter joined the operation, dumping water onto the roof. The flames too high for water jets to reach from the ground. The fire is thought to have been started by an electrical fault. Construction on the building had only recently finished. 3 of those killed were installing new lifts. Rescue crews evacuated hundreds of workers from the building just in time before it became an inferno. It's estimated the damage wreaked by one of Jakarta's worst ever fires will cost millions of pounds to repair. Neil Connery, ATN.
Although there's no real higher probability of having a fire in a modern office building than there is in any other sort of multi-storey building, if you do have a fire, it's likely to be a more expensive, more damaging fire.
Oh indeed, yes, there is a much wider implication as far as business interruption losses are concerned, over and above the pure property damage as far as the structure and the contents of the building are concerned.
The LPC test has been running for only 13 minutes. The glass facade is about to give up entirely. The inner glazed panels have fallen away. The outer pane of the glazed spandrel is about to fail. Hot smoke is pouring through the opening and it's about to burst into flames. The curtain wall has failed. The weak link has broken. Dr. Louise Jackman is the project manager.
What was important about these tests was we were looking at a fully three-dimensional test regime, rather than looking at a standards test which exposes a single flat surface of a curtain wall system. We were looking at a three-dimensional scenario where our curtain wall was joining with our floor slab and our fire, a real fire, was affecting the curtain wall as well as the joints between the curtain wall and the floor slab. We're using a range of sensors. We're using thermocouples to measure the temperature within the enclosure and also on the facade. We're measuring the mass loss rate of the crib so we can understand the size of the fire and link the fire size to the time of failure. We're also measuring the displacement of the facade so that we can look at how the facade moves, how it moves in towards the fire and how it moves out as the framework heats up. Many measurements were taken so that we could find which bit was failing and at what time it was failing. This information is subsequently being used to model fires, how they develop and how future failures might happen in curtain walls.
The LPC test has been running for 14 minutes. The remaining spandrels are about to fail. The outer window panes are barely attached and are about to shatter to the ground. The next story of the building, the one above the initial source of the fire, is now well alight. The frame supporting the glazing is being burnt through. In this particular test, the panel spans the concrete floor slab, giving a direct path for fire spread. When the spandrel is fire resisting, the situation is slightly improved. It's 20 minutes since the fire was lit. The fire test is over. What are the findings?
What we see here is the average temperature in the enclosure for a number of the tests. Test 11 is shown by this black line. You can see that at 900 seconds, which is the time of failure, the temperature in the enclosure has peaked to over 600 degrees. We also ran the test with an office fire load where we replaced the wood crib with office furniture. And in this test you can see that the temperature increases to a much greater value, over 1,000 degrees, and it all occurs much quicker. However, when we ran the test enclosure with a sprinkler enclosed, the temperature in the compartment never gets much above 100 degrees during the whole period of the test.
When office furniture was substituted for the wood and plastic crib, the outcome of the tests was quite different. The two fires were essentially the same in terms of their fire loads, but the furniture was more widely dispersed in the room and had a greater heat release potential due to its greater surface area. The initial fire growth was similar. However, with the furniture, the fire spread towards the windows. The glazing suddenly failed in just 6 minutes. At this point, flashover occurred, and all the combustible surfaces became involved in the fire, resulting in a much higher compartment temperature and taller flames up the outside of the curtain wall than had been previously seen. The Loss Prevention Council's series of fire tests have conclusively demonstrated that installing sprinklers can prevent fire spread in an office scenario and minimise damage. After the sprinklered fire test, the facade of the building had hardly been affected by the fire. The glazing was barely damaged. Only one crack was found in one pane of glass. The aluminium frame was structurally sound, and so was the framing detail. The convected heat of the fire was reduced sufficiently to prevent fire spread via the facade and through any unplanned flues. What are the findings? Unfire-stopped gaps give an immediate path for fire spread. Primary failure occurred because of the inherent weakness of ordinary glazing to fire. Fire-resistant spandrel panels survived longer and thus kept fire stopping in place, delaying internal spread and providing a barrier for external upward spread. The dispersion and surface area of combustibles were found to be as significant as fire load when assessing the risk of fire spread. Fire developed and spread externally before fire service intervention would be possible. Ceiling-mounted sprinklers kept compartment temperatures low enough to prevent significant damage to the curtain wall. The fire tests have further led the LPC to recommend that designers, contractors and business managers should select fire-resisting curtain wall constructions where possible, install and maintain suitably designed fire stopping, reduce the chance of fire by good management and maintenance, select appropriate protection based on a risk assessment, Rapid fire spread and falling debris, as seen in the tests, present real hazards to people, property and business continuity. Consult insurers as soon as possible to seek assistance with a risk assessment process. Keep fire service access points clear and maintain installed facilities like wet and dry risers and fire service lifts. By far the most effective means of protection was shown by the tests to be sprinklers. These should be chosen for all high-risk projects. Experimental records of the fire test programme are available from the LPC, and as a result of the tests, the LPC has drafted amendments for inclusion in the design guide. The costs of fire are measured not just in the direct cost of fire itself, but in the often catastrophic indirect costs of businesses destroyed, lives disrupted, or even ended. The LPC test programme has equipped everyone involved in the design and construction of curtain wall buildings with new weapons in the fight against the destruction caused by fire.